So we have to revisit redox reactions and balancing them. So this is a review from Chem 1A. So one way to remember how these things go is oil rig. So oxidation is loss of electrons, reduction is gain of electrons. So that's one way to define it. We can also think about it this way, that an oxidation is an increase in the oxidation state, and a reduction is a decrease or a reduction in the oxidation state. Okay, so oxidation state goes up, reduction, oxidation state is reduced. You have to have oxidation and reduction occurring together. And for such a reaction equation to be balanced, we have to have mass balance and charge balance. Sometimes you can do this by inspection and come out just fine, and other times it's a lot more complicated than that. So we use the half reaction method. We break the equation into two half reactions, we balance them separately and then put them back together. So we also have to review oxidation states. And as with many things, when you write out all the details, it makes it a lot more confusing than it actually should be. So here are the rules. Free elements have an oxidation state of 0. Monatomic ions have an oxidation state that's equal to their charge. The sum of the oxidation states of all atoms in a compound is 0. And if we add up all the oxidation states in a neutral molecule, it's 0. In a polyatomic ion, it equals the charge on the ion. In their compounds, metals have positive oxidation states. We see that group 1 metals always have an oxidation state of +1, group 2 always +2. So far, oxidation states are behaving almost identically to ion charges, right? If you have an ion, a monatomic ion, its charge and its oxidation state are the same number. They are different in concept, but the number's the same. And so we don't really even need oxidation states for those sorts of things. What we need it for is covalent compounds and for polyatomic ions. So nonmetals have oxidation states that are a little trickier because you look at like water, H2O. Well, there aren't any ions, there are no ionic charges, so how do you assign an oxidation state? So this is how we assign oxidation states for nonmetals. And this is based on concepts of electronegativity and all kinds of other things that we really don't want to go into, and so we can just look at this table. So you need to be able to do this without having the table in front of you. And we do this by thinking about noodles. Pho. Yum, right? Pho 765. Well, it's not a P, it's actually an F, but close enough, right? So Pho 765, FHO 765, fluorine, hydrogen, oxygen, group 7, group 6, group 5. So that's how you remember the order. The oxidation state that you assign to these elements is the same as the ion charge they would have if they were a monatomic ion. So fluorine as an ion has a -1 charge. Oxygen as an ion has a -2 charge, right? The group 5 elements as ions have -3 charges. So we don't really need to memorize these oxidation states. It's the same as ion charges. What we need is this order, and that's where Pho 765 comes in. So the way I think of this, because I tend to, personify all of these things, is you've got your metal ions and they've got their oxidation states, and then you've got this bickering among the nonmetals about who gets which oxidation state. This is the list of priority. If fluorine is there, she gets first choice. And then hydrogen gets the next choice, and then oxygen, then anybody in group 7, anybody in group 6, then anybody in group 5. And so you go through until you get to the last element in that compound, and that one has to make up the difference, because all of the oxidation states have to add up to whatever the charge is overall on that thing. If it's a polyatomic ion, like phosphate with a -3 charge, we need to make all of those oxidation states add up to -3. If it's a neutral molecule like H2O, the oxidation states have to add up to 0. Okay? So let's just throw a couple of examples in here. Maybe let's look at, oh, that's probably not a good one, but I was writing with the eraser, so it didn't work at all anyway. Maybe let's try carbonate. So carbonate ion. How do we assign oxidation states to carbon and oxygen? Well, there aren't any metals, so we go through the list, Fa765. No fluorine, no hydrogen, but there's oxygen. What charge would oxygen have as an ion? -2. So that's what oxygen chooses as its oxidation state. So the oxygen is going to have a -2 oxidation state. There are 3 oxygens in that polyatomic ion. Each of them is -2, right? So we have -2 and -2. So from the oxygens, we have a total of -6. There's one carbon. Carbon has to be whatever is needed for the things to work out. So if the oxygens together are pulling a -6 and we need -2 overall, then the carbon has to be +4. So the carbon then, send him off that way, is +4. Everybody okay with that? Remember this at all? Trying to think of something a little more interesting. That looks interesting. Neutral molecule. Who gets first choice? Hydrogen. There's no fluorine, so hydrogen. What does hydrogen want to be? +1. So how many hydrogens are in that molecule? 7. So there's 7 hydrogens. So we've got +1. That's not a 1. +1 times 7. And then we've got carbon and nitrogen, and so they're going to argue about who gets to be what. So who gets priority? Fluorine, hydrogen, oxygen, 765. Carbon doesn't even show up in the list. Carbon never gets, well, what would carbon want anyway, right? 5. So the nitrogen. Nitrogen's going to be -3. So we've got a -3 from the nitrogen. There's only one of those. And we've got these 2 carbons. So if we add up what we've got so far, we end up with +4. And overall, this has to be 0. We have 2 carbons, so they must each be +2. 2 carbons at +2 will give us overall a -4. Thank you. -2. And so that'll give us -4, and those will add up to 0. This isn't hard math, but it's just kind of fiddly and icky. Okay, so on to this half reaction method of balancing. Ideally, you would start by assigning oxidation states to all the atoms, identifying what's being oxidized and what's being reduced. Practically speaking, you don't really need to do that. If you have a real complicated equation, you might have to do that, but much of the time it's really obvious what things go together, and so you can kind of skip that one. Then we separate the overall reaction into two half reactions, one for the oxidation, one for the reduction. And it's great if you recognize which one is oxidation, which one is reduction, but to balance the equation, you actually don't have to even do that, but you do have to separate into two half reactions. So how do you balance those half reactions? First, you balance with respect to mass, balance everything other than hydrogen and oxygen. Then you balance oxygen by adding water, and you balance hydrogen by adding H+. This is for aqueous reactions. So there is water available, and there's H+ available. Then you balance each of the half reactions with respect to charge by adding electrons. So what we're trying to do is we're trying to make each side of that reaction have the same charge. They don't have to be zero, but you can't start with a +2 charge and end up with a 0 charge. Overall, you have to have +2 and +2. So you add electrons, however many you need. Do that to both half reactions. Then we're going to add those two half reactions back together. So we need to make sure that the number of electrons lost in the oxidation is equal to the number of electrons gained in the reduction. So sometimes you need to multiply one or both of those half reactions by a number. Add them together, cancel out the electrons and other things that might cancel out, and then double check that it's actually balanced. So those are the steps. Let's practice. So this slide, we have sort of a short list here of what we're supposed to do. Since we didn't just cover, like in 1A, when I do this in 1A, we had just covered oxidation states, and so we don't review that too much. Here, everybody's a little rusty on that, so I'm going to go ahead and we'll look at the oxidation states. So what's the oxidation state for aluminum there? We're starting with the reactants first. So this aluminum is 0. And the aluminum over here is +30. What about this copper ion? +2. And this over here, 0. So what's being oxidized? The aluminum is going up in oxidation state. And the copper ion is being reduced. So we need to separate these into two half reactions. So aluminum is going to be transformed into aluminum ion. There's no way we can make aluminum into copper, right? So the aluminums go together and the coppers go together. So aluminum solid is going to go to aluminum ion. And copper ion is going to go to copper metal solid. So I pulled this apart into two half reactions. We need to balance those with respect to mass. Looks to me like they're already balanced. Yeah? So that's fine. And we have to balance with respect to charge. This first half reaction, on the left there's 0 charge, and on the right there's a +3 charge. So we're going to make the two sides equal in charge by adding electrons. So how many electrons do I need? 3. And I'm going to put them over here, because then the 3 negative charges and the 3 positive charges add up to equal 0, which is on the other side. In this reaction, I'm going to put my electrons on the left side, because I had 0 on the right and +2 on the left, so I need to add 2 electrons in there. You should end up with electrons added as a product on one half reaction and as a reactant on the other half reaction. And if it's not working out like that at this point, something else is wrong. Because this is losing electrons, this is being oxidized, this is gaining electrons, this is being reduced. The reason that this equation is not balanced as written, it's balanced for mass, but the charges don't add up. Because 1 mole of aluminum releases 3 moles of electrons. 1 mole of copper ion will only accept 2 moles of electrons. And so that doesn't work out. So we've got it balanced with respect to charge. Now we need to figure out what can we do so that the number of electrons released here is equal to the number of electrons gained over there. So we're looking for least common multiple of 2 and 3 is 6. So we need to make both of these have 6 electrons. So this top one, I'm going to multiply everything by 2. So 2 aluminum atoms, 2 aluminum ions, and then this becomes 6 electrons. The other half reaction, I'm going to multiply by 3, so I get 6 electrons, 3 copper ions, and 3 copper atoms. You okay with that? Now we're going to add them together. So these 6 electrons that were produced got used up. You could kind of think of that as an intermediate. They don't show up in the overall reaction. I should probably switch colors here again. Let's go to purple. So these guys cancel out. They don't show up in the overall reaction. In this example, nothing else cancels out. Purple too. So I'm just going to copy down what's on the left side. So I've got 2 aluminum atoms, or 2 moles of aluminum atoms, and 3 moles of copper ions. It's going to make 2 moles of aluminum ions and 3 moles of copper atoms. That's the balanced chemical equation. Anybody have any questions about that one? Okay, let's do one that's more fun. Not much more fun, but a little bit. Balance this redox reaction in acidic solution. And we'll get to why it's specifying acidic solution in a couple slides. So let's practice our oxidation states again. What's the oxidation state for H+? +1. And for chromium, 0. And in H2, 0. And chromium 2 plus? +2. It's kind of lame. It is what it is. So I'm going to split these into 2 half reactions. The hydrogens are going to be together in one half reaction, the chromiums together in the other half reaction. So here's my H plus and H2, and I've got Cr and Cr2 plus. And you can save yourself some trouble later by leaving a little bit of space here in case you need to put a coefficient in there. Are these balanced with respect to mass? The chromium one's fine. The hydrogen one isn't. Here I've got 1 hydrogen ion and 2 hydrogen atoms in a molecule. So I need to put a 2 in front of my H+. Now we balance with respect to charge. So this first one, I've got 2 plus on the left side, and I've got 0 on the right side. So I want both of those to end up with 0. So I'm going to do 2 electrons over there. And then chromium going to chromium 2 plus, I need to put 2 electrons over here. These examples are ending up with both sides being 0. That's not always the case. So Here I've got 2 electrons and 2 electrons, so I don't need to multiply anything. So I can go through here, and the electrons cancel out. The electrons should always cancel out. If they don't, you've got a problem. Stop and fix that. Then copy down what's left. 2H plus aqueous plus chromium